Welcome everyone. I apologise in advance for today. It's raining quite a lot outside, so apologies if the audio is even worse than normal. So today we're going to look at amines. We're going to start off by looking at a couple of the prerequisites, so what do we need to know before we start this topic, and then talk about what amines are, how we name them, how amines can act as bases, and nucleophilic properties of amines, as well as how we make them. So what do you need to know before we get on with this topic? Well, we need to be familiar with some of the bonding because we will be discussing that. Nucleophilic substitution, you need to be kind of aware of certainly a basic understanding of that. And likewise, we will be discussing to some extent carbonyl chemistry. So if you've not revised much of that yet, please do that before now. And also the structure of benzene, because we will be discussing that later on. So, what are amines? Well, the easiest way to think of amines are of like organic relatives of ammonia, NH3. So this is ammonia over on this side. So NH3, so I've got nitrogen, hydrogen. So that's ammonia. So what we do in amines is one or more of these hydrogen atoms, so shown on my diagram as white, are replaced with some kind of alkyl or hydrocarbon group. So here we can see in this first one, we've replaced one of the hydrogens with a CH3. When we've replaced one hydrogen with an alkyl group, we say that this is a primary amine. So I denote primary as being one with a kind of superscript 0. How would I write this? So if we then substitute a second hydrogen, so let's substitute this one off here, and we're going to replace it with another methyl group. This time, because we've substituted two hydrogens, this is a secondary amine. And I would write a formula, which as I've done there. Okay, and obviously I've got an extra hydrogen here. I can replace that with another group here. So this time, and because I've replaced three of the hydrogens, this becomes a tertiary. So short chain amines, like these, tend to be soluble in water. But as the chain gets bigger, so let's make a big chain here. So this long one, what, 1, 2, 3, 4, 5, 6, 7 carbons long, this one may not be soluble, okay, because the non-polar hydrophobic chain is just not soluble enough. So even though you can get some hydrogen bonding going on up here, which is why these things are soluble in water, then it just won't be enough to dissolve. Okay, so longer chain. Longer chains are insoluble. Okie dokie. Right, one other thing to think about these is they've got quite a distinctive smell. Okay, they're not nice. Okay, anyone who smelled ammonia knows it's pretty pungent. Okay, it's used as smelling salts to wake boxers up after they've had their head bashed in for a while. But these other ones, probably these ones, similar-ish to ammonia, but the longer that they get, so these trimethylamine, triethylamine, they get really horrible sort of fishy, rotten fish kind of smell about them. They really are awful. I learnt this. I accidentally poured some down a sink once and ended up being sucked back in through the air conditioning and went to the managers on the business floor, and oh god, it was so much trouble. Anyway, yeah, you know about it if you start using these things. Right, okay, let's move on. Right, naming amines. Okay, nothing too clever about this. It's just the same as we would do pretty much every other organic molecule, whether it's an alcohol or whatever, that you go through the same steps each time. So first step is you're going to identify the longest carbon chain, which is bonded to the amine nitrogen. Okay, this becomes important because obviously we're going to be naming it an amine. You're going to identify any substituent groups here. So these more than likely be alkyl chains if you were asked to name an amine. Now you're going to number the parent chain. So that's the longest carbon chain we've identified in step 1. And the amine is going to take the lowest number. And then basically put all the stuff that you've worked out together, making sure that the substituents that you might have in here, methyls, ethyls or anything else that's in there, make sure that they're in alphabetical order. Now, there are some cases where you might have other functional groups in there. So we will meet amino acids in a future topic. But in those cases, then it's the carboxylic acid which would kind of take priority in the name. So then we just prefix it with amino. Okay, so this would be 2-amino ethanoic acid. So I'll draw this out here just for fun. So there's my basic structure of my ethanoic acid. This would be the 1 carbon. This is the 2 carbon. So this would be 2-amino. So my amine group's going to sit there, and I will have 2 hydrogens as well attached to this first carbon here. Okay, I've shown them both sat at the top just because I put my number 2s at the bottom here. Okay, so here are a few examples to try. So here I've got 1 CH3 group. Then my CH3 is attached to my nitrogen here. And I've got 2 hydrogens attached to it. Okay, so this has got a 1 methyl group. So this one, methyl amine. Okay, unless you're American and you'll probably call it methylamine. Anyone watch Breaking Bad, this is the compound that they're all after trying to get in the later series. Okay, so moving down here, this one down here, we can see we've got 1, 2 methyl groups attached to this one. So this one is going to be a secondary, just out of interest. And I've got 2 methyl groups, so CH3. And just 1 hydrogen this time, you can see it there. So this one I've got 2 methyls. So this time I'm dimethylamine, or dimethylamine, dimethylamine. As long as you write it, doesn't matter how you pronounce it. So I've got 1, 2, 3. Now these are actually methyl groups, it's just that my 3D model that I've got here actually got the hydrogen shown kind of behind, so you can't quite see it, but it is in there, I promise. Those are still CH3 groups. So I've got CH3. So this is a tertiary. And I've got 3 methyl groups. Excuse me. So 3 means trimethylamine. Okay, nice and straightforward. We're just adding them in there. And then down here, there's my nitrogen here. And I've got 1, 2, 3 carbons in a row. There's only 1 hydrogen that's been substituted off ammonia here. So this again is a primary amine. And what we have is propylamine. Okay, so I've got 3 carbons in a row, so that's propyl, and it's going to be an amine. Okay, aromatic amines. So these are ones where we have benzene as a base. So here's my benzene. And I'm going to add on an H2 group to this. So this is an aromatic amine, so it must be directly bonded onto the benzene ring for this. Now, can get a little bit messy if you've got other groups stuck on your benzene ring. But this one here, this one's fairly straightforward. We're going to keep with our amine ending, and benzene rings often referred to as phenyl groups. So this one will be phenylamine. You might come across it as aminobenzene, and certainly it's not unheard of to see them like this, okay, but typically we would say phenylamine because we're sort of prioritizing the amine bit. So this, most of the chemistry that's going to occur on this is going to be around this amine group here. Okay, so we're kind of prioritizing it there really. So now we're going to discuss how amines can behave as bases. So just like ammonia, the lone pair on the amine means that it can accept a proton. So it can form a dative covalent bond or a coordinate bond, depending on how you describe those. So they're acting as bases. So let's say I've got methylamine here. If I'm going to react this with a proton, it picks the proton up and it gains a positive charge. So here I've now formed a quaternary ammonium compound. So this would be a methyl ammonium compound, and it will be balanced off with something like a Cl if it was from hydrochloric acid. So you might have a Cl minus hanging around on this left hand side. So this would be methyl ammonium chloride. Now, the basicity of amines and ammonia for that matter is all about how available the lone pair is. So the more available it is, the more likely it will then pick up the proton. So the availability of the lone pair really depends on how much electron density is around it. Okay, so the more enriched the density of electrons are around the lone pair, the greater the strength of the base. Now, primary amines like this methylamine I've got here, they've got one alkyl group attached to the nitrogen atom. Now, the hydrogen atom is slightly more kind of electropositive, okay, than the carbon atom. So this means that the carbon atom has kind of more electrons than it normally would do. So the electrons are pushed towards the carbon, and in turn the carbon will then push the electrons towards the nitrogen, and thereby increasing the kind of availability of the lone pair. So the alkyl groups will push the electrons towards the nitrogen. Okay, this is going to enrich the electron density around the nitrogen in general, and in turn the lone pair there. This is called a positive inductive effect. So we've just looked at how one methyl group can push electrons towards the nitrogen, increasing the electron density. Now it follows that secondary with two methyl groups or two alkyl groups will push electron density even more towards the nitrogen, enriching the lone pair even more. And likewise a tertiary with three groups that are able to push electron density towards the nitrogen, we would expect to be even more susceptible to or performing as a stronger base. So in general terms, primary are less strong than secondary, less strong than tertiary. Now there is some sort of complications that if these alkyl chains, if it wasn't a CH3, say it was a CH2 with more carbons on it, then all these extra carbons in there, we've got this longer chain here. This can actually reduce the solubility of the amine. So in aqueous solution, it's not going to be able to accept as much protons, just simply because there's not going to be as much in solution. It's just not soluble enough. You know, it'll be floating around on top, you know, like an oily layer or something, because it just doesn't dissolve. It's only a finite amount will dissolve in the water. Now, they do like to ask you to compare base strengths of them, so relative base strengths. So here I've got an aromatic one, so this is phenylamine. Here I've got ammonia, and the one at the end here, this is 1, 2, 3 carbons, so this is propyl amine. Now, we've got to compare these. So we're using ammonia as kind of the reference, okay? So we're saying this is kind of middle ground. We're comparing the other two to it. So what we've just said previously is that if we've got an alkyl group, such as this propyl group here, it's going to push electrons towards the nitrogen and enrich the lone pair that's going to be on there somewhere. Okay, so there's my lone pair. So this is going to get a little bit further from the nitrogen atom, it's more easily able to pick out a proton from solution. Now, ammonia also has its lone pair. It's got no inductive effect in this one particularly, because it's just all the same kind of thing, and that's what we're comparing it to. But phenylamine, so if we remember what happens here, so in my benzene, oops, I've got my delocalized ring of electrons. Now what can happen is that the lone pair, I'm just going to draw it sat on the top here, from the nitrogen actually becomes delocalized into the ring. Okay, it helps stabilize the ring. It pushes electrons into it. It actually activates the benzene ring in this to actually make the benzene more likely to undergo electrophilic substitution. So here we've got a case where the electrons, and make sure you say that they're in the lone pair of nitrogen. So these are going to be delocalized, right at the bottom of my tablet here, delocalized into the ring. So what's the consequence of this? Well, if they delocalize into the ring, then the lone pair is less available, or less able to accept a proton or a hydrogen ion. So in terms of relative base strengths, well, we said that the propylamine is greater than the ammonia, but likewise the ammonia is going to be greater than the phenylamine because it's been delocalized into the ring. So make sure you're talking from point of view of both of these when you talk about this. So the propylamine is that the alkyl chain, so what did we say? It had a positive, that's a positive inductive effect. So it increases, I'm going to really run out of room here, increases electron density, maybe on the nitrogen, or of the nitrogen lone pair might be a better way of describing it. So then it is more able to accept a proton. Okay, so amines can be nucleophiles. It shouldn't be too much of a surprise. So say I've got just a simple amine here. I've got my lone pair. This lone pair is going to be attracted to areas of a positive charge. So say I've got, for example, chloromethane here. So my lone pair is going to be attracted to the delta positive carbon of my chloromethane. Okay, so it's going to act as a nucleophile. It's going to be attracted to regions of nuclear or positive charge. So that would be one example. The other one might be if you have a carbonyl, because we've looked at these before. So we know that within a carbonyl compound we've got a polar bond here. So this might be, let's just call it ethanol here, for example. So in ethanol we may get a lone pair coming in attacking the carbonyl group here. Probably looked at it when, for nucleophilic addition reactions where we've got to make an amide from an acyl chloride. Okay, so just always be thinking that this is a nucleophile. So amines can be nucleophiles, my handwriting's appalling, or they may be acting as bases. So be careful, look at the context of the question, what it's asking, which one is going to be most likely. Okay, what are they going to want you to talk about? So how do we make amines? Well, there's two main methods that we need to know about making aliphatic, so just alkyl amines. So we've got nuclear substitution of halogenoalkane, as I kind of alluded to on the last thing we looked at. Then also we've got nucleophilic substitution again, but this time it's of a cyanide ion on halogenoalkane rather than ammonia. Okay, so these are two ways of getting in there, but this second one is actually a two-step synthesis, so you've got to bear that in mind when we look at these. Right, we'll start off with nucleophilic substitution of a halogenoalkane with ammonia. So let's just get one in here. So I'm going to have chloromethane. I've kind of looked at this before, so we'll just do this in a little bit more detail. There are complications with this one, so you've got to try and keep up with this. And it's with ammonia NH3. So what is the reactive part? What's going to happen? Well, I need to think about where my electrons are. So they're going to start off here in a lone pair on the nitrogen. So where my electron's going to move? Well, think about what we've got up here. So we've got a delta positive carbon, delta negative chloride there. So our electrons are going to move from our lone pair towards the carbon in the chloromethane. So as this comes in and forms a new bond between the nitrogen and the carbon, carbon's then got 5 bonds, so it needs to ditch one of the bonds. And chlorine's a good leaving group, so the electrons are going to move from the carbon-chlorine bond to the chlorine. So now we've made this compound here. So I've got my carbon now, it's just attached to 3 hydrogens and then joined onto the nitrogen that's come from the ammonia. Now if we notice for the nitrogen here, it's got 1, 2, 3, 4 bonds. Okay, so if that's got 4 bonds, then it's kind of lost an electron. Okay, so it's put both its lone pair electrons over here into this new bond with the carbon. So the nitrogen has essentially lost one of its electrons to form that covalent bond, so it's got a positive charge. So the nitrogen here at this stage has got a positive charge. So we're going to have to lose this positive charge. So how are we going to do that? Well, one of these hydrogens is going to get lost. So the electrons from one of the nitrogen-hydrogen bonds is going to return to the nitrogen. Okay, so it's then going to form a neutral molecule. So here I've got my methylamine that I have now made. So we do need to account for all the other atoms that we've got in here, and this is a little bit trickier. Okay, so what actually happens, and you don't need to show this in mechanisms, however if you show it incorrectly you will get it wrong. So what happens, how does this hydrogen over here how does this come off the amine group here? Well, it is actually abstracted, so removed, by another ammonia molecule in there. So the other ammonia molecule has a lone pair. So this lone pair can actually form a bond with the hydrogen that we are removing. So here I've just shown it attached to the ammonia here. So essentially what I've made here is NH4, put it in brackets. This is going to have the positive charge now. Because remember, the electrons have moved to the other nitrogen over here, so this is a proton it's picking up, positively charged species, so I've formed NH4+. So this is positively charged. What else have we got? Well, we've forgotten about the chlorine that was over here. Okay, this chlorine now is going to buddy up with this ammonium ion to make ammonium chloride. Okay, so we've made our methylamine and we've made ammonium chloride. So we actually did a reaction using 2 ammonia molecules. Okay, so you've got to remember that when you do a reaction mechanism, a reaction equation, I beg your pardon. So here are the bones of the equation. So remember, our chloromethane reacted with ammonia, but we needed 2 for the reaction to occur. So we made our methylamine, but we also produced our ammonium chloride. My PC's slowing down today. My pen's got a bit laggy. Okay. So my chloromethane reacted with 2 ammonia. That's an A in there, not an E. To make methylamine and ammonium chloride. Apologies for my handwriting, it really is terrible. Okay. Okay, so here I've just rewritten the equation. So we've showing that we are forming methylamine in this case. So the reaction between chloromethane and ammonia to make methylamine. Now, a few moments ago I mentioned about amines being nucleophiles. So they have a lone pair on them, which is able to react with certain species. And one of those species that we mentioned were halogenoalkanes. So in this reaction that we have here, we have a halogenoalkane. We have chloromethane. So if there are still chloromethane species in here, then they are potentially going to be able to react with the stuff we have just made. So here's my methylamine with its little lone pair. So I could do a reaction now on this. So I'll just show that down here. So just redrawing them out here so I can see my lone pair on my nitrogen of my methylamine. So this would be attracted in to the carbon there. The carbon then would be having 5 bonds, so it doesn't like that, so it's going to lose the chlorine because chlorine's a good leaving group, and it's going to kick that out there. So now I'm going to be making a new molecule. So here I've just drawn out my intermediate. So don't forget, this nitrogen now has a positive charge. So we need to get rid of the positive charge. So like before, a nitrogen-hydrogen bond will be broken with the electrons returning to the nitrogen, releasing the proton, okay? And it would be taken away with another ammonia or whatever else we've got in here. And I will be forming our product here. And now we've got 2 methyl groups. So this would be dimethylamine, dimethylamine. So is that the end of the story? Well, not quite, because we still have an available lone pair on this nitrogen. So this might also be attracted to the delta positive carbon on a chloromethane. So these could then carry on and do another reaction, and so on. So let's just break this down a little bit. So we've just said that any methylamine that we produce could react with more chloromethane to produce dimethylamine. Now I'm for the purpose of this, I'm just going to be focusing on the amine that we're making. So this dimethylamine that I have now made still has a lone pair. So this can then react with another halogenoalkane, so another chloromethane, and that's a 2. And I've got a hydrogen, whoops. So this time we would get another substitution. So now we've formed trimethylamine. Okay, and we've got some accompanying other stuff, but again I just want to focus on these because this nitrogen now, it still has a lone pair. So even though we produced a primary, a secondary, we've produced a tertiary. So now this nitrogen with its lone pair can still go on to react again. Apologies, I've done it in a different order this time. CH3Cl. So now we've got 4 methyl groups. Okay, this time there's no spare lone pair. This is over. Because the nitrogen has now formed a bond to 4 different carbons, each carbon in a separate methyl group, now it's got a positive charge. Okay, so this then has formed a tetramethyl ammonium compound, and seeing as we've got so much chlorine lurking around, it will be tetramethyl ammonium chloride. So this is a quaternary ammonium salt. Okay, so there we go. So we can make amines reacting a halogenoalkane with ammonia, but it has its problems. It creates, or it forms, a mixture of products. So this can be a little bit of a problem. How can we get around it? Well, we find an alternative synthesis. And here we go with our alternative synthesis. Okay, so this time we are going to react a halogenoalkane with a cyanide ion. This is a 2-step synthesis, so it's a 2-step reaction. So it does require a little bit more recall on your part when you're answering the questions, but the questions are worth a little bit more as well, so there's more they can ask about them. So let's start off with our halogenoalkane again. So here I have my chloromethane. I'm going to use this as my example just because it's the simplest one. And this time our nucleophile is going to be a cyanide ion. Okay, a cyanide ion has got a triple bond with a nitrogen, as I'm sure you remember from the past, and it's got a negative charge and a lone pair. Okay, so there we are good to go. So I've shown our delta positive and delta negative on our halogenoalkane here, just to help us. We don't need to show them, but it's just to help us show what's happening. And our electrons are going to move from our lone pair, and they're going to make their journey over here to form a new bond with the carbon. So remember, be very precise, or as precise as you can, with the curly arrows that you're drawing. The carbon's then forming 5 bonds. It doesn't like that, it wants to get rid of some, so it's going to break the bond between the carbon and the chlorine, showing the electrons coming from the middle of the bond preferably, just so there's no question, to the chlorine, and then we're going to form our new product. I'll quickly do this. So here I have shown my new compound that I've made. So this is ethane nitrile. Okay, so we've now made an organic compound containing the cyanide group that we started with over here. So this might have come from potassium cyanide or something like that. Now we formed our nitrile, and remember to be careful if you have to name these. You need the whole lot, not ethane nitrile or anything like that. Ethane nitrile. So okay, so we've got this nitrile. We've not got an amine, so now we have to do something with this. So now we're going to use this in a new reaction. It's no mechanism, it's just a reaction you need to learn. So, my nitrile, my ethane nitrile. What I want to do is I want to turn this into an amine. Ethyl amine. So we can see here I've got one carbon, two carbons, 3 hydrogens, 1 nitrogen. Over on this side, 2 carbons, 3, 4, 5, 6, 7 hydrogens and my nitrogen. So I've added some hydrogens to this. So how many hydrogens have I added? I've got 3 to turn into 7, so I've added 4 hydrogens. And now it is okay for us to show hydrogens in square brackets here. A bit like when we do an oxidation reaction, we can show O's in brackets to show that it's oxygen that's come from an oxidizing agent. This time we've got hydrogens that have come from a reducing agent. So you need to know what the reducing agent is. Okay, you've got a choice of a couple you can do for this one. So the reducing agent may be, I call it lithium aluminium hydride, lithium tetrahydridoaluminate, I think, or something like that. It's a bit of a mouthful to say, and in order to save the number of reducing agents that you need to remember, to keep it kind of easy to remember, really, you could say I'm going to use hydrogen with a nickel catalyst. Okay, so this is the one that I tend to prefer, okay, because you've got two things you're talking about here. So you've got hydrogen with a nickel catalyst. In terms of other conditions, you might want to say, if you're going for this one, you're going to do a second step with dilute acid to help neutralize that off. And this one, usually they'd ask for 2 parts. If they wanted any extra bits here, you probably want high pressure and high temperature. Okay, I would remember this one. Sodium borohydride isn't, sodium tetrahydridoborate is not strong enough. So you've got to choose something different. So I'm going to choose this one. So there we go. Now we've made an amine. Now one thing to notice, here we started with a carbon, okay, carbon chain of 1 carbon in length. When we finish down here, we've got a carbon chain 2 in length. Okay, so this becomes kind of synthetically useful because adding nitriles in allows us to build our carbon chain up a bit. Okay, so we're increasing the carbon chain. So you might want to do that to make new molecules. But also when you do the synthesis topic later on, this is one of the things to look at. So if you're going from step A to step B, have you increased the carbon chain length? If you have, then be switched on. Okay, so it might have involved a cyanide, okay, a nitrile synthesis step. So how do we make aromatic amines? Okay, so here I've got a nice little benzene ring that I've already started drawing out. And what we would do is we would, first of all, you're going to stick on a nitrile group. So as you would have covered in aromatic chemistry, so nitric acid, sulfuric acid, to generate a nitronium ion, which you then could do electrophilic substitution on the benzene ring to produce this. Then what we're going to do is we're going to have a reduction. Now you may have covered this already in aromatic chemistry. Should have got another one of my pre-prepared hexagons ready. And we want to make a NH2. We want to make our phenylamine. So if I want to do this, I've got to get rid of the oxygens and I've got to add some hydrogens. So if we've got oxygens and hydrogens related, you will hopefully be thinking, I've got some water going on somewhere and I'm going to be adding some hydrogens. Now, here, because the way that we use this, we use tin and HCN. So HCN, well, we do not use that at all. We use tin, SN, and hydrochloric acid. And it's conc hydrochloric acid as well. Okay, so it's concentrated hydrochloric acid and tin. And we're going to add some hydrogens to get rid of our oxygens. So 2 oxygens on this side. So I'm going to produce 2 waters over here. And I've got 2 plus 4, so it's a total of 6 hydrogens. So I can just show that, a bit like before, like that. So here I'm reducing my aromatic amine to form aromatic nitro group, sorry, to form my aromatic amine, my phenylamine. Here, and key thing is your tin and your hydrochloric acid is your reagents here. So your tin is just a catalyst, hydrochloric acid is the reagent. Now, you may come across an issue where you need an extra step in this. Because it's done in acid conditions, what we might have actually made, and I'll just trim these down a little bit. I'll leave this here. Instead of it being NH2, you might have made NH3. Cr-, so you make a salt here. So to get rid of this, you might needed to neutralize this off with some OH- to actually get to the final product. This isn't a step that you see very often, but just bear it in mind just in case they do throw a wobbler at some point in the future. Okay, yeah, so that's making amines. Right, so we'll have a go at a practice question. So this is just the AQA website, and we'll have a look at paper 2. So if we go down here, we can find one from 2019. So this is the paper here, and we will just open this up. And question 1 is all about amines. So let's go and dive in and have a closer look at this. So here we are with question 1. So give an equation for the preparation of 1,6-diaminohexane by the reaction of 1,6-dibromohexane with an excess of ammonia. Okay, so this is a key thing that we've got to remember on this one. They've mentioned it for a reason. So let's just draw some things out. So we want to make, we'll start with dibromohexane. Let's start with that one. 1, 2, 3, 4, 5, 6. And it's dibromohexane. So I'd have a Br there and a Br there. So I'm going from that, and it's diaminohexane. So 1, 2, 3, 4, 5, 6. And I want to make my amine like this. So I'm going from here to here, so I'm going to be replacing the bromo, so it's a substitution, nucleophilic substitution, and I'm going to be using ammonia. Okay, so we know that because it kind of told us this down here. But we've got an excess of ammonia, so we just need to plan that in. So we could say I've got Br, and then I've got CH2, and I have 6 of these, and then another Br. Okay, so my 6 CH2s, because remember our terminal carbons here have been replaced by one of the hydrogen has been swapped out by a bromine, so there's only 2 hydrogens on it, and I'm ultimately going to want to make my diamine. Okay, so there we go. So that's what we want to do, and we're going to be adding in some ammonias. But we need to work out how many of these we're going to add. So we definitely need 2 for either end of here, but also remember we've got to remove the bromines, and we've got some spare hydrogens. So we've got 2 bromines to get rid of, and we're going to be losing it as NH4Br. Okay, so remember the excess ammonia tells us we've got lots of ammonia in there, so it's going to remove those. So now we're at, what are we, 1, 2, 3, 4 of these. So 4NH3. So moving on to the second part of this question. So this is a mechanism and it's given us something to start with. So it's given us an ammonia. So I'm going to start by putting my lone pair on, make it nice and clear. I've got my ammonia there. So the carbon that we're interested in that's attached to the bromine, so we've shown the bond breaking here already. So we need to get these electrons coming in to form a bond here. So this would be the first part. So we've got the lone pair coming in to attack the carbon that's attached to the bromine that we're going to lose in this case. So this is not the end of it, so we need to move on a little bit. So on the next part here, so let's say I've put my ammonia here, and I normally like to show all my hydrogens coming off here now because it lets us think about what's happening. So 1, 2, 3, 4, 5, 6, and then we have another NH2 at that end. Okay, so here our nitrogen is going to positive charge. So we need to kind of lose a hydrogen from this one. So we're going to lose some electrons from here and they're going to go to the nitrogen, and then that would release this hydrogen ion. So then we've got our hexane diamine, I beg your pardon. 1, 2, 3, 4, 5, 6, that's the nitrogen. H2. So that's that bit there. Okay, so we've got this part now where we want to suggest structure of a cyclic secondary amine that can be formed as a byproduct in this reaction. Okay, so cyclic secondary, and I would read this as being secondary as in 2 carbons attached to it as well. Okay, so thinking about that. Right, I'm going to clear my screen here. There we go. So instead of using this, you don't have to do this mechanism, I'm just showing you this just to show you where I'm coming from. Instead of it being an ammonia that's coming in, what could happen is the amine group at this end of the molecule that we're starting with can actually be the nucleophile. So this would come in and attack the carbon there. So then what does this form? Well, I've got a nitrogen. This will be attached to a hydrogen. So this will be attached to 1, 2, 3, 4, 5, 6 before it attaches back to itself. So good luck writing this one out. So 1, 2, 3, 4, 5, 6 before being attached back to the nitrogen. So we've got 1, 2, 3, 4, 5, 6. So it is a 7-membered cyclic ring, and we'd call this a heterocyclic ring because it's got something other than carbons in it. So it's a bit tricky one to draw out. So this 7-sided heptagon, I guess we got. And then my nitrogen. My first attempt was probably better than that. Anyway, there we go. So that would be our answer for the next one. So this 7-membered heterocyclic ring, which would be a byproduct of the reaction. There we go. There would be other options perhaps. So you could perhaps use 2 of these coming together, opposite ends, making a mirror kind of thing, but it is the one that I would go for. Right, so here we are at part 3. So 1,6-diaminohexane can be formed in 2-stage synthesis. So we should be really thinking about the cyanide synthesis from this because we're starting from 1,2-dibromobutane. So if you just drew these out, they are so 1, 2, 3, 4 with a bromine at that end, and we want to get 6 carbons in here. 1, 2, 3, 4. Yeah, I did get it right. And ultimately we want the diaminohexane. So you've got an amine group and 1, 2, 3, 4, 5, 6, and then another amine group at this end. So that's the ultimate goal that we're going to get, but it's a 2-stage synthesis. So we're making something, then we're moving into something else. So we're increasing the carbon chain length. Now I mentioned earlier about increasing the carbon chain length by 1, and that's when we'd be using a cyanide to do it, but this time we're increasing it too, but that's because we've got a bromine on each end of the molecule, so one will be increased by one, the other end will be increased by another one. So what we're going to be making is Cn. 1, 2, 3, 4, like this. So if you were doing proper skeletal formula, you wouldn't have shown it as like this, but I'm just showing the substitution process of this. So the reagent to go from here to here, we're going to be wanting to use something like potassium cyanide, sodium cyanide. Don't use hydrogen cyanide because they don't like it, because we should be using this stuff because it is safer. And the condition that we would do for this, we want to make sure that it's in the same state. So we may not be wanting to put it in just water because this stuff up here won't dissolve. So maybe some kind of alcohol and water mixture, aqueous ethanol, let's just say, or aqueous alcohol or something along those lines. So the aqueous means that our cyanide is going to be dissolved, and the ethanol will make sure that the dibromobutane is dissolved. So then we've got stage 2, which is this one here, and this is the reduction stage. So what reducing agents are we going to use? Well, I would say H2 and a nickel catalyst. So it may be that they want, this is the reagent, this is the condition. You could say high temperature, high pressure. They may ignore this in the answer. I don't know why that didn't draw. I'm suspecting this is the bit that they're after here for the marks there. Alright, explain why 3-aminopentane is a stronger base than ammonia. Right, so I'll clean that page and I will move down a little bit. So 3-aminopentane is a stronger base than ammonia. Why is this? Well, 3-aminopentane, so the lone pair on 3-aminopentane, that is an A, I'm not very good with this pen, is more available to accept a proton. Okay, so why is this? So that's probably one mark, so we've got to be talking about the lone pair. The second mark is, why is it more available to accept a proton? Well, this is because we've got the positive inductive effect from the alkyl group on there. Okay, so these are the two kind of factors that we're talking about here. I'll just about squeeze this on down here. It's not linked to amines as such, but it just shows how we can tie in a few different things together. So this is the isomerism topic. So justify the statement that there are no chiral centers in 3-aminopentane. So let's draw this out. 1, 2, 3, 4, 5. So here, 1, 2, 3 is where we're going to get our amine group. Just about squeeze that in there. So here we can see we've got the same group attached. So you'd also have a hydrogen on there. So you one amine group, one hydrogen, but then the other two groups on there are both ethyl groups. So you could just simply say there are not 4 different groups There's not 4 different groups attached to any carbon in the whole molecule there. Okay, and then that's that question done. Right, so what have we done today? So we've looked and discussed what amines are and how we name them. We've looked at the base properties of the amines, so to determine what factors affect how strong a base they might be. So thinking about the availability of the lone pair on the nitrogen and being quite specific that we're talking about the lone pair on it. looked at how that lone pair dictates the nucleophilic properties of amines, and we saw how amines can then react with halogenoalkanes to make even more substituted amines, and that linked into how amines are prepared. So there was 2 key methods for aliphatic, so that's just with no aromatic groups in, so that's with reaction with ammonia and halogenoalkanes, or there's the 2-stage synthesis where we take our halogenoalkane and react it with a cyanide ion and then a subsequent reduction to make the amine. And we also looked at aromatic amines, how we would reduce a nitrobenzene to make a phenylamine type compound. So that's it for this video. Please let me know if you've got any suggestions and what have you, and I will see you again next time.